Hey guys, and welcome to another video. In this video, what we're going to be doing is we're going to go through a few different examples of how to differentiate. So for those who aren't familiar with differentiation, it is essentially trying to find the gradient at a specific point on a function that's not linear. If you want more information about how differentiation works, feel free to look into the limiting chord process or the limiting chord theorem. That really steps through what differentiation is, but this is our shortcut way of how to differentiate. So in short, if you want to differentiate a function, what you need to do is multiply your powers to your coefficient, and then you subtract one from your index or your power. Okay, so I'm going to go through a few different examples of this. Nothing too crazy, just some really nice simple examples. And I'll do them using different notation. Now, the reason why I specifically chose to do examples with different notation is for you to be really familiar with the way it can show up. So sometimes they use f of x, and the differentiated answer would be as f dash x. Or it could be in the form of y equals, where you have dy dx, the difference in y over the difference of x, which is, of course, our gradient that links back to it. So it could be in a different format, and sometimes you see it as y equals, and then the differentiated answer is y prime. So I wanted to just show you those examples and what that looks like in written form. So we're going to go through a bunch together, and let's just go straight into it. So here's my examples. My first one is f of x equals x to the power of 8. Now, you might be thinking, there's no coefficient. Now, don't be silly. Of course there is one. The coefficient of this particular function is 1. So if you can never see like a number in front, I still to this day always put a number in the front, which is 1. Okay? So what we're going to do is we're going to multiply my coefficient of 1 to the power of x, which is 8. So 1 times 8 is 8. Now the x stays, it doesn't go anywhere. And then I'm going to subtract 1 from the index. So 8 take 1 is 7. Now I'm not leaving my answer like this. I haven't got it equal to anything. Do you see that? So what you need to do is actually write down in this, to match this notation, put that prime symbol on there, just to indicate that you have differentiated the function. Okay? And you could just leave it like that. That's your answer. Okay? Differentiated. Here's my second example. You're like, oh wait, hold on. I don't have a coefficient and I don't have a power. Again, of course we have one. Coefficient's 1, the power is 1. Okay? So if I want to differentiate this, what I'm going to do is I'm going to multiply my power to my coefficient. So 1 times 1 is 1. Now I'm going to subtract 1 away from my coefficient. 1 take away 1 is 0. So it's x to the power of 0. Now, if you leave it like this, it's okay. It is not the ideal. But what we're going to do is hopefully realize x to the power of 0 is 1. So that's the same as 1 times by 1, because there's an imaginary times in there. Imaginary times in there. 1 times 1 is 1. So simple as that. Now let's put in our notation. It is y. So we're going to use the notation here of dy dx. Okay? So make sure you always got it equal to something. Sometimes I usually write that first, but I just wanted to show you just the process. Okay? So normally when I see the function, the first thing I'll do is write the corresponding notation. Okay. So just note, by the way, that if you ever have a function that has just a letter, let's say, it is going to be 1. Okay? If you had a number in front of that, so let's say you had y equals 3x, your differentiated answer would be just 1 times 3, which is 3, x power of 0, which is just 3. So the x essentially disappears if the original function was just x on its own with a power of 1. So just a good kind of thing for you to note as well. Okay, let's do our next one. d dx. This is asking us basically to differentiate. Okay, so d dx of 2x cubed. Let's do it. So I'm going to write dy dx is equal to 2 times 3 is 6, x to the power of 2, because 3 take 1 is 2, and then you've also got 2 times 3 is 6. So those were those are where that comes from. Okay. Next one here. Okay, I've got some negatives. This makes it a bit different. So let's try it. We're going to write the differentiated function is equal to negative 5 times by negative 4 is positive 20, because negatives and a negative make a positive. The x stays there. Now I'm going to subtract 1 from negative 4. Please note that negative 4 take 1 is not negative 3. On our number line, if you go back, you've got negative 4. Remember, when you're adding, you go that way. If you're subtracting, you're going that way. So in fact, you're actually ending up at negative 5. So please don't make that mistake. That's the worst sometimes, when you realize you're like, oh, that's wrong. This is a fine answer. Now, just note that most questions will ask you to leave answers positive indices. So let's do that. So if it's a negative, we're going to put it on the bottom. So 20 over x to the power of 5. Because if we remember, if it's x negative 1, it just becomes the reciprocal. All right. So let's do a few other ones. So here's one of just a constant. We have no x. What do? So if you imagine, if there's no x, that's the same as x to the power of 0, because x to the power of 0 is 1. So it's imaginary, put it in there. 0 times 5 is 0. X power of negative 1. Okay, then we're getting warmer. But if we remember, anything multiplied by 0 equals 0. So it doesn't even matter that the x to the power of negative 1's there. The answer is 0. So if you have a constant, it disappears. It becomes 0. It is essentially ignored. So there is a constant there, but you just get rid of it, because even when you showed it out, anything times by 0 is 0. Okay? So those are my examples, and I hope you enjoyed. Thanks very much. Bye.